let's take a look at the graphs of logarithms. Logarithmic functions are pretty interesting because they have this unique relationship that we've explored a little bit with exponent and root functions, but they're also pretty difficult to gain an intuition around. I think one of the helpful ways to develop this is by looking at the behavior of their graphs. I will be graphing the two most frequently used types of logarithms. These are the logarithm with base 10, literally referred to as the common logarithm. Now this is written out simply as log log without any base specified. This can be a little bit confusing because it looks like you don't know what base you're working with, but just remember that we're working in a number system that has base 10, so when you're working with logarithms and the base isn't specified, the automatic is going to be base 10. That's your sort of starting base, I suppose you could call it. So here I'm going to start by sketching out these axes. So I've got my y-axis defined here, and then I'm going to draw my x-axis. We notice though that my y-axis is really far over to the left. So the reason why I'm doing this and why I'm not leaving much space to the left of the y-axis is because the graph of these logarithms is only going to be defined in the first and fourth quadrants. So I only need to make room for those positive x values. Here I'm going to be plotting the point 1, 0. Now this is a point that shows up on every graph of logarithms that we're going to work with. It's a pretty important point to remember, and it can be quite helpful. I'll get into why that shows up so often later on. Now I'm just going to sketch out the general shape of what this graph looks like. It's quite a soft curve. You can see it's slowly decreasing in velocity as x increases. And you can also see as x approaches 0, it's approaching the y-axis, but it never actually touches the y-axis. That's an important thing to take note of. Now, let's look at the graph of the natural logarithm, the next very common, well, not common, we've already looked at the common logarithm, but the next most frequently used logarithm. Now, this is a logarithm with base e, and it's written out as ln, so this is our natural logarithm. So here, again, we see that I haven't left space in those second and third quadrants because this is not going to show up in those quadrants. We're only working with the positive x values. And we also have this specific point, 1, 0, that's showing up again. Now, here's the difference. When I'm sketching out this shape, it looks slightly different. So with this base of e, which keep in mind e is less than 10, it's stretched quite significantly. So here are some things to remember, and then try and see if you can develop an idea as to why this graph on the right looks stretched. So these graphs are on the same scale, and e is less than 10. So the base of the graph on the right is less than the base of the graph on the left. Examining these graphs leads us to some generalizable observations about the graphs of logarithms. Now, let's look at the limitations on these observations. So these only apply when we're working with log base b of x for any positive value of b that's not equal to 1. The reason that we don't work with base 1 is because when you have a base of 1 and you raise it to any exponent, the value that results from that is going to be 1. So a log base 1 would be undefined at every point of x, except for at x equals 1, where we're going to see a vertical line occurring. The first generalizable observation that we're going to work with is this value of log base b of 1. It's always equal to 0. Basically, what this means is that any graph of y equals log base b of x will have the point 1, 0. Now, this is because any value b raised to 0 will be equal to 1. The next observation is that the graph of log base b of x always has a vertical asymptote at x equals 0, or the y-axis. It's never going to cross that axis. And finally, for b greater than 1, as b decreases, the graph of log base b of x will stretch vertically. Now, this is happening because for a lesser value of b, a greater exponent y will be required to raise it to that same value of x. Now, the opposite transformation occurs when b is between 0 and 1. This is because for those values, a greater exponent yields a smaller value.